All right, here we go. Unit 5, Lesson 7. We're going to be starting one of my favorite topics in all of calculus. It's a topic where if things have been difficult for you to visualize and picture, this whole unit on motion is going to give you an entire other way to think about the concepts of the derivative and the second derivative that has physical application. So you're going to have to bring yourself back to your ninth grade physics because we're going to start talking today about position, velocity, and acceleration and how applying calculus to those concepts can really deepen your understanding of them. So, first, let's talk about this word velocity. Velocity, in a very casual sense, as we're going to find out later, they actually do not mean the same thing. But we often, in casual language, we think velocity means speed. We're going to find out later that it's not exactly true. But for right now, you can think of velocity as just it's your distance over time. If I say the car is going 60 miles per hour, that's a distance over time, 60 miles per 1 hour. And if we consider where that velocity function came from, like where does distance come from? Well, distance is just the change in position, right? It's just some position B minus some position A. So if you have a distance function, P of t or X of t or S of t are all common, where t is the time input and P of t is how far you are away from some starting point, we can apply the same calculus reasoning of AROC average rate of change and IROC instantaneous rate of change to velocity. If I calculate your average velocity, what I'm doing is I'm saying, what is your ending position minus what is your starting position, P of B minus P of A, over the change in time, over the change in time. And so that would be, what's your average speed? How fast were you going on average? But now that we know calculus, we know there's another kind of velocity, not just average velocity, which requires two positions, but instantaneous velocity. Like if you pointed a radar gun at a car, your instantaneous velocity, right? If you have your position function, if you have some function P of t that tells you where your car is located left and right on some track, right? Your instantaneous velocity is the slope of the tangent line at that function, the slope of the tangent line, or the derivative of the position function, or velocity, right? It's your instantaneous speed, okay? So, like I said, these are going to give you ways to really visualize the derivative in a way that has more of a physical application. So here's an example. Let's say a particle's position is given by the function P of t is t cubed minus 9t squared plus 24t. If I wanted to find the average velocity of the car from time t equals 1 to t equals 3, well, I would just do P of 3 minus P of 1 all over 3 minus 1. And so again, I'd just be plugging in here. I'll just kind of fill this out really quickly, but I'm not even going to do the math out because I know you're all capable of that. That would be 3 cubed minus 9 times 3 squared plus 24 times 3, right? Like all of those from position 3 minus the same thing from position 1, 1 cubed minus 9 times 1 squared plus 24 times 1 all over 2, right? And we don't need to do that, but you could calculate this and it would be some kind of, maybe I'm making up units here, maybe it'd be like miles per hour or something like that. But now with calculus, we can also calculate this different thing. We can calculate the instantaneous velocity, and this is going to be a lot easier, a lot less math to do here because we only have to plug in once. If P of t is my position function, then P prime of t, right? The change in position over time at an instant, right? This is the velocity function. So velocity is the derivative of position. You're going to hear me say that a million times today. 3t squared minus 9t, minus 18t, just using the power rule here, plus 24. And so V, making it right, P prime of 2 equals V of 2 equals whatever 3 times 2 squared minus 18 times 2 plus 24 is. I'm kind of letting you in on a little like calculus secret here. If this were an open-ended response, you could stop here and you could stop there. As soon as you're down to just numbers, you could stop. So you get the idea. That's how we would calculate instantaneous velocity or average velocity. So let's move on to the second concept here, acceleration. If instantaneous velocity is the derivative of position, instantaneous acceleration is the derivative of velocity, which makes it the second derivative of position. So really important concept here. Acceleration is the change in velocity at an instant, so v prime of t, which is the second derivative of position, since velocity is the derivative of position. All acceleration is, right? It's how fast are you speeding up or slowing down, right? If you're accelerating, you're pushing on the pedal, your velocity is getting faster. So same idea here. If you did average acceleration, right? If you did average acceleration, it would be v of b minus v of a, velocity 2 minus velocity 1. So we'll call that ending velocity minus beginning velocity all over the change in time. Versus if you did the instantaneous acceleration, like I said, instantaneous acceleration, it would be the derivative, right? That's the change in velocity at an instant over time, or the second derivative of position. So if I wanted to calculate the average acceleration of this particle, same equation here, well, I know that p prime of t from this last problem is equal to velocity, and that's, again, using the power rule, 3t squared minus 18t plus 24. If I wanted to find the average acceleration, well, I would need to do, right? I would need to do velocity at 3 minus velocity at 1 all over 2. So I would take this velocity function, right? Average acceleration. The biggest mistake, I guarantee you're going to make it at some point, everyone does, is they go to calculate average acceleration by doing acceleration at time b minus acceleration at time a. But what you found there is the change in acceleration. There's a word for that. It's actually called jerk. We'll go over that just as a like brief aside. They do have names going down. It's like jerk, snap, crackle, and pop. I'm not kidding. It's actually snap, crackle, and pop are their names. But if you wanted to find average acceleration, that is the change in velocity, not the change in acceleration. So your average acceleration would be velocity at 3 minus velocity at 1 all over 3 minus 1, or 2. So you would have to plug in to the velocity function that I just did there. So this would be like 3 times 3 squared minus 18 times 3 plus 24. All of that minus, I'm kind of running out of room here, but you get the idea. 3 times 1 squared minus 18 times 1 plus 24 all over 2. But if I just ask you for the instantaneous acceleration, now I'm talking about the second derivative of position, how fast position is changing, right? So the velocity, the derivative of the velocity function, how fast your speed is changing, that is your acceleration. And so this would be the derivative of velocity, which would be acceleration, using the power rule again, would be 6t minus 18. And so the acceleration at time 2 would be 6 times 2 minus 18. The acceleration at time 2 would be 12 minus 18, or would be negative 6. So your acceleration at that point in time would be negative. Okay, so let's look at this example here. If we have some function s of t, which represents position, and this is why this is called particle motion, of a particle moving along the x-axis. So really, you can imagine like a little bug or a little car, and it just moves left and right. That's all it does, is moves left and right. And its distance from home is actually represented, it's a little confusing, but its distance from home is represented by this function here, s of t. So the farther up we go, the farther to the right this bug goes. The farther left we go, the farther down we go, the farther to the left this bug goes. And so let's look at a few examples here. At which point is velocity equal to 0? Okay, so let's remember here that velocity is the derivative of the position function. And so that's going to be 0 at the points. That's going to be 0 at the points where position is not changing, where you're not moving left, you're not moving right, where position has a horizontal tangent line. Okay? And so if I were to do a justification here, it would be because P of t has a horizontal tangent line, but I want to get us moving through this here. At what point does acceleration equal 0? Okay, so acceleration is the second derivative of position, is the derivative of velocity, and that's acceleration. Your second derivative equals 0 at inflection points, right? It's where your first derivative is neither increasing nor decreasing, where you're going from concave up to concave down. All right, and so if you think about speed as the slope of this line, so the slope of the tangent lines at point C, for 1 second in time, not even a second, for an instant in time, your slope isn't increasing of your tangent line, nor is it decreasing. That is going to be at point C. That is going to be at point C. I'll go back here and label that this happens here at B and D. Okay. On what intervals is velocity positive? Okay, velocity equals the derivative of position. So velocity is positive when the slopes of my tangent lines are positive, or when position is increasing. And so that will be from A to B, as well as from D to, it's not really labeled there, so I'll say from D to infinity. Okay. Well, let's just say to E, just to make it simple there, from A to B and D to E, but really it's like whatever, if this goes on forever or not. When is the particle's velocity negative? Well, that would just be when position is decreasing. So the derivative of position is velocity. And so position is decreasing, velocity is negative from B to D. And finally, on what intervals, when is the particle's acceleration positive? So remember, acceleration is the second derivative of position. And so we're looking for when position is greater than 0. Sorry, when the second derivative of position is greater than 0. So P of t would be concave up. And that's going to happen, concave up, right, like a cup, is going to happen from C to E. Versus acceleration will be negative. We'll do this in a different color. Acceleration will be negative when P prime, double prime of t is less than 0. So P of t is concave down. And that will happen. That will happen from sort of A to C if we're just using those points there. So from A to C. Okay, last final summary page here. When we talk about particle motion, the most common thing to imagine, like I said, is like a train or a bug going along a track. And there's a few important things to keep in mind here about what this means. Position will be measured here in left and right. And like I said, it's a little bit confusing at first because it'll be the y coordinate of any graph you're given, but it just means left and right motion. So here are the things you want to keep in mind. If velocity is positive, the particle is moving to the right. If velocity is negative, the particle is moving to the left. And remember at the beginning of this video where I said speed and velocity are not the same thing. Speed is just the absolute value of velocity. And the reason for that is when I say how fast your car is going, there's no such thing as 60 miles per hour north versus 60 miles per hour south. If I just ask you how fast the car is going, it's just 60 miles an hour. So, in terms of this bug here or this car, we don't really care whether it's moving left or right when we talk about speed. Speed just means how fast you're going, and it doesn't have a direction. And so, when we ask about speed, speed is increasing when velocity and acceleration have the same sign. Speed is increasing when velocity and acceleration have the same sign. Speed is decreasing when velocity and acceleration have, sorry, that should be opposite signs. When velocity and acceleration have opposite signs. The reason for that is, right, the way that I think will help clear things up, velocity is basically saying which direction am I walking and how fast. So am I walking left or am I walking right, and how fast? So just literally imagine yourself walking left or right. Acceleration you can imagine as at that moment in time, wind starts blowing. Is the wind blowing in the same direction as you and helping you and making you go faster? Then your speed is increasing. Is the wind blowing against you and blowing at you and making you start slowing down? Then you will be slowing down. Your speed will be decreasing. And so the last example here today, if we have position is t cubed minus 9t squared plus 24t, so just working with this same function here, is the speed of the particle increasing or decreasing when t is equal to 2.5? So what I would do, first I would get my velocity function, and as I say, my velocity using the power rule is 3t squared minus 18t plus 24. And my acceleration will just be the derivative of that. So acceleration will be 6t minus 18. And I want to know, when is speed increasing or decreasing? So I need to know both velocity and acceleration. If they're in the same direction, speeding up. Opposite direction, slowing down. So I could just plug in 2.5, but sometimes you'll be asked for intervals of increasing or decreasing. So I want to show you that here. If we take this velocity function and we factor it, so first we factor out a 3, this will be 3 times t squared minus 6t plus 8. And we further factor it to 3 times t minus 4 times t minus 2. What that tells us, if we create a sign chart here of velocity, if t is less than 2, well then both of those parentheses would be negative, your velocity would be positive. If t is between 2 and 4 seconds or minutes or whatever this is, then the left parenthesis would be negative, the right would be positive, you'd have a negative velocity. If he was greater than 4, if t was greater than 4, both would be positive, you'd have a positive velocity. And so we're going to do the same for acceleration, right? So we've got intervals where velocity is positive. This basically means moving right and moving left and moving right again. Versus for acceleration, if we do this same thing and we factor out the 6 times t minus 3, well, acceleration only has one changing point, is at 3. If t is less than 3, acceleration is negative. If t is greater than 3, acceleration is positive. So acceleration negative, acceleration positive. And like I said, you can imagine this as, I'll call this wind left, like the wind is blowing this particle left or starting to push against it in the leftward direction, versus the wind right. And so if I think of at t is equal to 2.5, I am moving left and the wind is left. So if you imagine this car, it is both moving in the leftward direction, and I'm not really good at drawing this, but and there is a wind blowing against the car that way. So we are, in fact, speeding up. And so, formally, without the like wind or pushing analogy, speeding up because V of 2.5 and A of 2.5 have the same sign. Kind of running out of room to write that, but have the same sign.